Hello everyone. Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we'll go over the contents of week 12. Before that, we'll look at the questions of week 11, just revise a few concepts and then go over the questions of week 11 and then the contents of week 12. Okay, so let's begin. Okay, so dynamic stability, we had been looking at this for the past 2-3 weeks now. So dynamic stability is when the aspect of time comes into play. Okay, so we had first derived the equations for point mass in 2 degree of freedom in the 2D case. So we had x, y and the velocities in each direction. We had 4 equations of motion. And then we moved on to an aircraft. So for the aircraft you have for longitudinal case you have CL and CM. CL is the coefficient of lift, CM is the pitching moment coefficient. Okay, so initially, like I had said, we begin with CL naught and CL alpha into alpha. That was the approximation for the lift coefficient. Then when the control aspect came, we studied CL delta E into delta E. Similarly for the pitching moment, first it was just CM naught plus CM alpha into alpha and then CM delta E into delta E. Okay, then when the aspects of dynamic stability came, we looked at two new terms, that is CLQ, CL alpha dot. Similarly, CMQ and CM alpha dot. And we've discussed in depth about which each of them should be, like how they are QC by 2V, why we've done QC by 2V, how we have non-dimensionalized each term because CL and CM are both non-dimensional parameters. Okay. Then we saw the effects of this pitch rate. Effect of pitch rate Q produces a change in the angle of attack at the tail. Right? So it produces change in the angle of attack at the tail. How did that produce changes in the lift and the moment? So when there's an increase in angle of attack at the tail, so if there is an increase in angle of attack at the tail, there's an increased lift component, right? So you have a delta L which increases. With increase in angle of attack, you have increased lift, which in turn produced a pitching moment. Now it produced a pitch down moment, okay, which is why you have this negative because our sign convention says that negative pitch down is negative. Okay. Then we saw how it is similar to spring mass damper system, a typical spring mass damper system, where Cm alpha is like the stiffness coefficient K and Cmq is like the damping coefficient C. Okay, so Cm alpha stiffness coefficient, it is the rigidity. Okay, so it is the resistance towards any perturbation. Alright, Cmq is the damping coefficient. It tells you how fast it will come back to equilibrium or if it will come back to equilibrium at all. You remember that the difference between static and dynamic stability was what? Static stability was the tendency to come back to equilibrium upon perturbing. Okay, what was dynamic stability? When the aspect of time comes, it will tell you whether or not it actually comes back to equilibrium. Okay, alright. Now next, we study the different types of forces, aerodynamic, gravitational, propulsive, and then we looked at the different frames in which these were defined, inertial and body. Okay, so what were the aerodynamic forces? Lift and drag. Gravitational is the weight, mass of the aircraft. Propulsive is the thrust. Okay, and then we saw the frames of reference that were necessary for this analysis. We have one inertial frame of reference and one body reference frame. What is the inertial reference frame? Inertial reference frame is centered at the earth. We are taking, for our case, we are assuming the earth-centered, earth-fixed frame as the inertial reference frame. It is not actually an inertial frame. We're just assuming it to be inertial because for our flight duration, for the duration in which we are performing the analysis, you can consider it to be inertial. Okay, you can consider it to be inertial reference frame, the earth-centered, earth-fixed frame. And then you have a frame of reference, body reference frame, which is fixed on your aircraft. Okay, so it moves with the aircraft. Now several quantities are measured in the body and some of them are measured in the inertial. So when we write the equations of motion, this Newton's equation, the Euler's equation, both of these equations are defined only in the inertial reference frame. Okay, so it is valid only in this frame. Now since many of our quantities are measured in the body frame, we require to formulate a relationship between these quantities in the body and the inertial frame. and their derivatives. Okay, so we're doing a dynamic analysis, so the derivatives also come into play. What is this relation? It is this. It's given by the transport theorem. Transport theorem. And we have derived this in 2 of the previous sessions, so you should be able to do it. If not, it's a fairly simple derivation. You should be able to do it. Just remember this, alright? This relation is very simple. Now we employ this relationship on our Newton's law of motion and the Euler motion to get these final two terms, sum of forces and sum of moments. Now these are just the quantities represented, their individual components represented in the different frames. Okay, alright. Now we move on to its individual equations. So when you expand this Newton's and Euler's equations of motion, you get 6 different equations, right? So you get Fx, Fy, Fz, and you get Lmn, which is the moment in the x, y, z direction respectively. Okay, so just expanding these two terms gives you the 6 equations, that is Fx, Fy, Fz and Lmn. Okay, then we looked at Euler angles. Euler angles psi, theta, phi, and we studied that the psi, theta should not be confused with yaw and pitch. They are the Euler angles. What are Euler angles? It gives you the orientation of the body frame with respect to the inertial reference frame. Okay, so it's not to be confused with the yaw and pitch, which are measured in the body frame. It's the orientation of the aircraft measured in the body frame, right? Not with respect to the inertial frame. Okay. Then we had seen where these Euler angles come into play. They come into play in 2 places. One is the gravitational forces Fg and PQR. What are PQR? What are PQR? The angular velocities, omega, right? So this is PQR. So these are the 2 places where the Euler angles come into play. Okay. Now we looked at the longitudinal dynamic stability. For that we analyzed only 3 of those 6 equations. Okay. So we analyzed 3 of the 6 equations. Then we studied the small perturbation theory, which is to take a body at equilibrium and then perturb it with a small quantity. Okay. So in our case, the equilibrium or the steady state is the trim condition. So all of these terms with the subscript 1 are the values measured at equilibrium. U1, V1, P1, Psi1, all of those. Okay. Then we studied stability axis. We had also done a couple of questions on this. Does anybody remember what the stability axis is, why we did this? Alright, so stability axis is chosen to be aligned with the incoming velocity vector. Why we do this? It greatly simplifies our equations. You can see that the elaborate equations in the first 3 are greatly simplified when it comes to the last 3 equations. Why is it simplified? Because several of your quantities are measured either parallel or perpendicular to the incoming velocity. Like lift is perpendicular to the velocity, drag is parallel to the velocity. Okay, so all of these rotational terms, that is sine, cos, all of them get reduced when you assume your axis to be oriented along the velocity vector. Okay, so this is the main reason why you have simplified equations and why we have chosen the stability axis in such a way. Okay. Then we studied each of those individual derivatives of those 3 equations of dynamic longitudinal stability. Okay, so Fx, Fz, M, and each of those small derivatives. Now the derivatives with respect to alpha dot and q are not given in Fx because they are negligible in that direction, but they are not negligible in the Fz and M directions. So you have 5 terms for Fz and M, while you have only 3 terms for Fx. Okay. Then we studied each of these derivatives separately. We analyzed them separately and formed an equation in terms of u dot, w dot, and q dot. Okay, so those are your final dynamic equations. This is how you arrive at those. Okay, so this is your final compact u dot equation. Similarly, you have one for w dot, and you have one for q dot. Now here, the negative sign that is shown here is because your lift, when it's produced in a direction that is opposite to the z direction, to the positive z direction, right? It is opposite to the z direction. So you have a negative sign there. So if this is your wing, the lift is produced in this direction. But we have taken our body axis z z-axis of the body frame in the downward direction, right, towards the underbelly of the aircraft. So the lift will have a component in the negative z direction. Okay. Then another important thing that we've seen was why we have an alpha dot. We have a q because we give a pitch rate. Why do we have an alpha dot? Because when you give the command for change in angle of attack, it doesn't immediately produce a change in angle of attack. Okay, it gradually produces this change in angle of attack. There is a gradual build up of the lift. It doesn't become, the angle of attack doesn't change immediately, instantly. Okay, it takes time. So you have an alpha dot. Another reason for alpha dot is the downwash. Can someone tell me what downwash is? We discussed this extensively, and when we had discussed this slide initially, we had this discussion before. Can someone tell me what is downwash? If any term here reminds you, just look at all the equations. Look at equations pertaining to alpha dot, so then you will find terms that might remind you of downwash. Can someone tell me what downwash is? What is downwash? Wingtip vortices, anything like that ring a bell? So it's this epsilon term, right? So we had studied epsilon is epsilon naught plus dou epsilon by dou alpha into alpha. I don't think I will discuss this again, but you should remember what downwash is. The wingtip vortices in the wake of the wing and then moves on to the tail, produces a reduction in angle of attack, reduction in velocity. Yeah? You just go over your notes of the previous lectures, then you'll be able to find this out. Okay. And the final set of equations, that is for q dot, final set of derivatives for q dot, and gives you your final equation in terms of q dot. So you have u dot, w dot, and q dot for longitudinal dynamic stability. Okay. Okay. Now you put them all together in the compact form that we had discussed and put it in form of a matrix. Then apply a Laplace transform considering this. Right, so that is one of the relations that you need to be aware of while taking the Laplace transform, and then you get it into a final compact form in this manner. So this can be equated to Ax equal to b, right? This is x, this is a, and this is b. All right, and then you can perform your matrix calculations using this notations. Okay, then we had seen, yes, when you solve this, how do you find the characteristic equation of this matrix? Yes. Okay, so how do you find the characteristic equation of this matrix? This Ax equal to b, how do you find the characteristic equation of A? Can someone tell me? How do you find the characteristic equation of A? Take its determinant, exactly. So you take determinant A equal to 0. Okay. When you do that, you get a fourth order equation. Correct? Yes? There is an S, there is an S, and there is an S square along the diagonal. So you get a fourth order characteristic equation. Now it has coefficients a, not to be confused. Okay, let's just, I've done this last time also. This is a different a. Okay, it's a different a. Okay, so when you write its characteristic equation, you have its coefficients capital A, B, C, D, and E. Now, in order to ensure stability of this equation, stability of the states of this equation, there are some criteria. The first criteria is all of these coefficients must be positive. And then you have something known as a roots table. Okay, roots table I think Sarah discussed extensively. So there is a roots table from which you get the second and third criteria, right? Second criteria. And the third criteria gives you some conditions in terms of Cm alpha, Cmu, Cl alpha. Okay, that's the relation that should be maintained for stability. Now, for this aircraft, for the longitudinal dynamic stability, it so happens that you have two distinct complex conjugate pairs of roots. Okay, so the four roots are two pairs of complex conjugates. One is the short period and one is the long period. So you have just A plus or minus IB, you have C plus or minus ID. Now, if magnitude of A is greater than the magnitude of C, can you tell me which pair of roots correspond to short period and which pair corresponds to long period? If the magnitude of A is greater than the magnitude of C, which pair of roots corresponds to the short period, which pair of roots corresponds to the long period? So the A plus IB corresponds to short period, right? So this is short period and this is long period. The one with the larger magnitude of the real part of the root corresponds to the short period, okay? Then we've seen how each of these roots, the equations associated with each of those roots can be compared to a typical second order system, which in turn gives you the short period damping ratio and the short period natural frequency. Similarly for the long period, okay? So you form equations with each pair of roots, compare it to a typical second order system, and then you get your natural frequency and damping ratio of each case. Alright? Then we had seen some approximations. So you have a short period mode approximation where you assume u to remain constant. U, the velocity u, you assume it to remain constant. What happens then is that the first row and the first column can be neglected, and so you get another set of equations, right? You get a reduced order set of equations, and this is that equation corresponding to short period mode approximation. Alright, and the corresponding natural frequency and the corresponding damping ratio are given in these two. Alright, so you know how to find that out. Just equate it to a typical second order system equation. What was the equation? S square plus 2 eta omega ns plus omega n square equal to 0. So equate each of these terms to its corresponding terms in the typical equation, and you can find the natural frequency and damping ratio. This can be done for any such approximations, okay, any such second order, any such pair of roots. Okay. Then you have this Fugard mode or long period mode approximation, where you assume alpha to remain constant. Okay, then your second column in the third row can be neglected, and then again you have a second order equation given by this. Again you compare it to a typical second order equation, you find out your natural frequency and damping ratio. You have a third approximation, that is a pure pitching approximation. Okay, so the assumptions made in that case are given here, and when you perform the analysis you get a second order equation, again equate it to typical second order equation to find out the this was a mistake, this is pure pitching. Okay, so you get the natural frequency and damping ratio. So this slide summarizes all the three cases. Just go over it, just remember these. Okay, you just have to remember, I think, the equations, or if you can do the main matrix, then it will be fairly easy. When you have the assumptions, you can make your own equations. You don't have to remember the natural frequency damping ratio, you can derive it fairly simply. Okay, so yeah, so this compares your short period, Fugard and pure pitching motions approximations. Okay, so now let's go over the questions. When the center of gravity of the aircraft moves rearward, then the effect on long period mode will be. What will be the answer of this? Will it be more stable as compared to last center of gravity position? If the horizontal tail area remains fixed, then only more stable as compared to last center of gravity position. Does not depend on center of gravity, less stable as compared to last center of gravity position. Which one will be the right answer? Which one will be the right answer? You've all done this quiz, right? You can also, I think the answer solution manual is uploaded. So can you look at it and tell me? So it says less stable as compared to the last center of gravity position because the damping derivative decreases and the dominant pole will move towards the right. Okay, when the dominant pole moves, so if you have your poles here and if it moves towards the right, if it moves here, so this was case 1 and this is case 2, if it moves towards the right, will it be more or less stable? The answer we just said will be less stable, right? So for stability, we know that these real parts must be negative, and when it becomes more positive or becomes less negative, it becomes less stable, right? So the real part of the roots must be negative. That was the condition for stability. More negative, more stable. Less negative, less stable, right? Okay, let's move on. Next question. Long period motion is given as, so they're giving you equation for the long period approximation. So given you the equation here. Now they've asked you to find out the damping ratio and undamped natural frequency. How do you find this? They've given you the equations, right? So you can find the characteristic equation. Once you find the characteristic equation, you can equate it to a typical second order system and find out eta and omega n. Can you do it and tell me? First, find out the characteristic equation. How do you do that? So if this is A, consider this matrix to be A, you have lambda I minus A, determinant of this equals 0. This is how you find out the characteristic equation, right? So try doing this and tell me what is the equation. If you find out the characteristic equation, just tell me, okay? Have you found the characteristic equation? Have you found out the characteristic equation? So let's just try doing this. So what do you get? You get lambda plus 0.03 9.81 minus 0.055. You get lambda here, correct? This determinant equals 0. So it's really simple, right? How do you find this out? Just find out the equation. So you have lambda square plus 0.03 lambda plus 9.81 into 0.055 equals 0, which is lambda square plus 0.003 lambda plus, can you multiply it and tell me? 0.539 equals 0, correct? Now equate it to typical second order equation. You take s square, you take lambda square. Lambda square plus 2 eta omega n lambda plus omega n square equals 0. So omega n is square root of 0.5. It's actually 0.539. Square root of that is, what is the value? .735 radian per second, correct? Now 2 eta omega n is 0.003. So eta is 0.003 by 2 into 0.735. How much is this value? How much is this value? Just calculate it and tell me. How much is the value? I'm getting something around 0.02, right? Okay, so it is 0.02 and 0.73. This is the answer. Let's move on to the next question. The long period motion is given as same process, right? Find out the characteristic equation, equate it to a typical second order system, the equation of a typical second order system, and then find out omega n and eta. Tell me this answer. Find out the characteristic equation and tell me. Have you found the answer? The period of the sinusoidal motion. How do you find the period? We know how to find out omega n and eta. How do you find the time period? If you find out its frequency, not the natural frequency, if you find out its frequency, you will be able to find out the period, right? What is the relationship between frequency and time period? Okay, let's try doing this. Again, try to write the characteristic equation. How do you do the characteristic equation? Lambda I minus A determinant equal to 0, where this is A. So what will it be? Lambda plus 0.03, 9.81, minus 0.055, lambda. Okay, it's the same equation. So what is the equation in the previous case? Lambda square 0. Now when you find out the roots of this equation, they will be in the form of A plus or minus IB, right? And this B will be the frequency of oscillation, correct? Will be the frequency of oscillation. Yes? Amplitude plus frequency, correct? So you find out this frequency, find out B. What are the roots of this equation? What are the roots? What is this A plus IB? What is A and B? What are A and B? just find the roots of the equation. So you have roots are minus 0.003 plus or minus square root of 0.003 4 into 39 by 2. So what are the values? Minus 0.015 plus or minus 0.73i, correct? So this b is 0.73, which is nothing but the frequency. Now when you know frequency, how do you find out time period? For any oscillatory motion, what is the time period? How do you find time period if you know frequency? So time period is 2 pi by omega, right? So you have 2 pi by 0.73. How much is this? .85, correct? Seconds. Or 8.55, sorry. 8.55 seconds, correct? So this is the correct answer. Let's go to the next question. The short period motion is given by, again they've given you an equation. The numeric values of A and B will be taking damping ratio and undamped natural frequency as 0 and 5. Damping ratio, eta is 0 and natural frequency is 5 radian per second. Again find the characteristic equation, equate it to a typical second order equation where value of eta and omega n are given, and find out the values of A and B. The same type of questions. Try doing it. Did you find out the characteristic equation? In terms of A and B. Okay, let's just do it. So if this is A, this matrix, lambda I minus A determinant is 0. Okay, so what do you get? You get lambda plus 1 minus 1 minus A lambda minus B determinant equal to 0. So what is the equation? You get lambda square plus lambda minus B lambda minus A minus B equal to 0. Lambda square plus 1 minus B into lambda plus minus A minus B equal to 0. Equate it to a typical second order equation to eta omega n lambda plus omega n square equal to 0. Okay, so now you do minus A minus B equals omega n square, which is 25, and 1 minus B equals 2 eta omega n, which is 0. So B equals 1. So minus A minus 1 equals 25. So A equals minus 26. Yes? So these are your two values, 1 and minus 26. That is, A is minus 26, B is 1. Yeah? Okay, so all of these questions, first you find out the characteristic equation, equate it to typical second order equation, and then you can find out whatever is asked, either the unknown coefficients or the damping ratio, natural frequency. Okay, now let's go to the next question. The short period motion is given as, again they're giving you an equation, the number of cycles to half the amplitude will be. How do you find this? How do you find this? Number of cycles to half the amplitude. You have that equation directly, right? For simple harmonic motion, you have that equation. So number of cycles is 0.1 by the frequency and then the amplitude, right? Modulus of the frequency by the amplitude, right? So in one of the this is 0.11. Okay, so one of the previous questions we had found out how the frequency and amplitude, the roots of the equation, right? So find out the characteristic equation, find out the roots of the equation. So you have something, the roots are A plus or minus I omega. So find out the roots of the characteristic equation, and then you can find out the number of cycles to half the amplitude. Okay, let's do this. Find the characteristic equation. Okay, so you have lambda I minus a determinant equal to 0, where this is a. So you have lambda plus 0.06 minus 1, 4.3, lambda plus 3, right? So what is the equation? You have lambda square plus 3 lambda plus 0.06 lambda plus 0.06 into 3 plus 4.3 equals 0, right? So when you simplify that, you get lambda square plus 3.06 lambda plus 4.48 equal to 0. Now what are the roots of this equation? Find out the roots of the equation. Again do so. Lambda equals minus 3.06 plus or minus square root of 3.06 square minus 4 into 4.48 by 2. What do you get here? What are the roots? What are the roots? Minus 1.53 plus or minus 4.16 I. Okay, so this is a plus or minus. Okay, this was a bar. A plus or minus omega I. Okay, so when you substitute it here, you get 0.11. Omega is 4.16. By a is minus 1.53. So what do you get this value as? 0.1, and which is when you round it off, what do you get? It's almost equal to 0. So number of cycles it takes to reach half the amplitude is 0. Okay, let's go to the next. Okay, I think we done this in the last class. Okay, for an aircraft, the roots of the longitudinal characteristic equation are shown in the figure. Right, so you have two pairs of roots as is expected. It's a fourth order equation. You get two pairs of roots. Okay, now let's look at the questions. The roots for short period mode are, which are the roots? So you have two roots here, you have two roots here. Okay, so are the ones circled ones? Okay, let's erase that. Are the circled ones the short period roots, or are the crossed ones the short period roots? The one with the larger magnitude of real part, right, is the short period. So which one is it? The circled ones, right? Oops. The circled ones. So those are minus 4 plus or minus 2i. Okay, natural frequency and damping ratio of the phugoid mode of the long period. So the roots are 0.002. So minus 0.002 plus or minus 0.1i. Now tell me the natural frequency damping ratio of the long period. I will not be solving this. We did this in the last class. Just find the characteristic equation, equate it to typical second order equation, and tell me the eta omega n. So this is omega n, this is eta. So it was s square minus sum of roots into s plus product of roots. Okay, and your equation was okay. Find out. Have you found out? Okay, I'm not going to solve this, so you know how to do this. Let's go on to the next question. Consider the following equation of a system. Find the range of k values necessary for dynamic stability. This again we had done in the last session. First case is that all the coefficients must be positive. So 1 plus k must be greater than 0 or k must be greater than minus 1. Okay. Next you have to make the roots table. Find out the roots table and do it. So you have, if these are a, b, c, d coefficients, your roots table is a, c, b, d, and then you have a1, b1, and all the entries in the first column must be positive. So a and b already are positive. You have to find out a1 and make sure a1 is positive. What is A1? A1 is 1 by B determinant of AC dt. Okay, so find this out and make sure that A1 is positive. This is what gives you the next condition on K. Did you find out A1? Have you been able to find A1 and the condition on K? Okay, so A1 is coming to be 1 plus K minus 9 by minus 3, and this should be greater than 0, which gives the condition on K should be less than 8. Alright, so this is the correct answer. K should be greater than minus 1 and less than 8. Okay. For an aircraft in first sight, it was flown from north to south, and in second flight from south to north. For both the flights, the indicated airspeed and altitude are the same. A steady wind was known to be blowing from north to south. Damping ratio for first and second flights are eta 1 and eta 2 respectively. Which of the following options is correct? It hasn't updated. Okay. Do let me know if the slides are not changing. Okay, so there is some lag in the internet connection. Okay. So this is one question, and what about the natural frequency? This is another question. Think about it sometime and get back with an answer. Okay, think about it. They've asked you for both damping ratio and natural frequency. Read the question carefully, look at your notes about the damping ratio, natural frequency, look at the equations, see what factors it depends on, and tell me the correct answer. sorry about that, there was a break in the internet from my side. So if you look at the equations for omega n and damping ratio, Nastral frequency and damping ratio, neither of those equations have anything to do with direction of velocity or oncoming velocity at all, right? So neither omega n nor the damping ratio will change with any of the factors mentioned in the question, right? So it will remain same for both. Damping ratio, omega n, both of them remain same. Okay, next question. A canard surface is introduced in an aircraft keeping all other dimensions intact. Which of the following statements is correct? What is a canard? It's a surface that is added ahead. So if this is your wing, this is your tail, surface that is added ahead of the wing. This is wing, tail, canard. And say your CG is somewhere here. So as far as static stability is concerned, will it be stabilizing or destabilizing? So this is the lift of the wing, lift of the canard, lift of the tail, right? So lift of the wing is destabilizing, lift of the tail is stabilizing. We had done this before. So I think in canard we had discussed a couple of questions. The lift of the canard is again destabilizing, right? So static stability will decrease. What about short period damping? Will it increase or decrease? Again, look at the equations. Look at the equation for short period damping. Where is it? Yeah. Look at the equation for short period damping and tell me if this increases or decreases with the introduction of a canard surface.
staying.